Okay, so here's what we were talking about last time. We're doing the chain rule, right? And just rewinding just a little bit, here's the first version of the chain rule we wrote down. The idea being that, well, look, we have a rule for how to talk about the linear approximations or differentials, depending on what you want to call them, for a function like this. And then if you just precompose and divide by dt, that turns into this, which very nicely, just will observe, that is an immediate relationship between the derivatives, the various partial derivatives of that purple function and the various component derivatives, you might say, of the yellow function, right? And so the composition derivative can be computed from individual partials. So this is highly reminiscent of the single variable chain rule. This is the multivariable, our first version of the multivariable chain rule. Then I introduced a different point of view. Now we'll go through those details again because it takes time. It's a premium, of course, in this class, which is you can think of this in terms of how changes propagate. A change in t propagates through changes in x to then cause changes in z, which we argued gives you this term. And then, but at the same time, as t changes, that causes changes in y, which propagate on through, and then from that you get changes in z, and that gives you another term. And I think this is a really, really handy way to think about it also. So, take your preference. I'm going to give you a different way to think about it in a few minutes. But certainly from a day in, day out convenience of computation standpoint, this one's really nice. So make sure that you digest this one. Okay. And then we did an example. I think this is where we ended last time. Here's z as a function of x and y, and here are those derivatives, partial derivatives, that is. And then here's the precomposed function, x and y as functions of t. Here are those partial derivatives, combine as previously discussed. And there you go. Okay. All right, now a little point of detail here. Reasonable question might come up, often comes up, is, okay, so how do I evaluate this at a given point? How do I evaluate this at, let's say, pi over 6? Okay. Think about the details. What do I mean when I say at pi over 6? Notice I am thinking of z as a function of t. That means this is a value of t specifically. This is not a value of x and y and t, right? I mean, that wouldn't make any sense, right? So this is a value of t. So, okay, well, what that means is this value of t, sure, but notice that means if I know what t is, I can plug into the formula and see what x is. And likewise, I can plug into this formula and see what y is. Right? So x is that and y is that. And so, so you have a couple of options in terms of how you evaluate this. One thing you can do, I think this is a great way to do it, is whatever value of t you're looking at, use that to subsequently compute your values of x and y, and then just plug those in directly to this formula. Now, a different thing you could do, and I don't really like this, I think this is a cheap trick, but it's fine, I suppose, if you really want to. Different thing you could do is actually take this formula here for x, the actual formula, and plug it in there for x. And then take this formula for y, the actual formula, and this, and plug it in for y in there, and turn this expression here into a great, big, huge expression exclusively in terms of t. I mean, look, you could do that, right? But it's kind of bypassing the convenience of this already having been sort of simplified. We've taken advantage of the fact that we know what x is, right? So why throw that away? It seems sort of counterproductive to me. Okay. Last comment I want to make, and even going back to just to right here, And I want to remind y'all, this is one of the big sort of, I'm going to call it philosophical point of the class, is this is not a class about answers, it's a class about ideas, right? And furthermore, on exams, part of the question that you're responsible for is to look at the question, interpret it, what I'll call appropriately, right? Make sure that you can determine what the point of the question is, right? How is this a multivariable calculus problem? And then how you can demonstrate your understanding of the relevant multivariable calculus ideas that, of course, clearly are what I'm looking for in a multivariable calculus class, right? Okay, so with that in mind, here's something that students like to do sometimes, and that would be entirely unacceptable and not at all okay, and probably 0 partial credit if you were to do it on an exam, and that would be to take this formula and plug it into there, right? And then take this formula and plug it in to there and to there. And turn this into a great big huge function of, z is a great big huge function of t. And then just use single variable calculus to take the derivative, the single variable calculus chain rule. Now that will get you the answer, right? But keep in mind, that's not what this class is about. This approach of turning a multivariable calculus problem deliberately into a single variable calculus problem, it bypasses the obvious intent of the question. The obvious intent of such a question is, I want to see if you are proficient with the multivariable chain rule. Right, so anyway, think this kind of thing through, make sure to, to digest that this is actually a requirement of the course. Okay, so what happens if you have more than 2 intermediate variables? I hope this comes as no surprise, but if there's more than 2 intermediate variables, then there are correspondingly number of terms, correspondingly number of paths along which changes can propagate, right? Each one of which gives a term. Just like the argument that we made here. Here, 2 paths, because there's 2 intermediate variables, and therefore 2 terms in the chain rule. Likewise here, if there are n intermediate variables, then there are correspondingly n paths, and therefore n terms in the chain rule. So, morally equivalent argument. Okay. Yes?
How do we arrive at this chain rule?
Well, okay, so there were 2 ways that we thought about it up here. One is to use linear approximations, right? And the other is to think about propagation of changes through paths, right? Yeah. Okay. Okay, now here's another twist, and this one looks a little bit more worrisome. I made the observation when we were doing partial derivatives that the realization there is that input variables are really where the worry is. The worry, if you have multiple input variables, that's something you've got to actually take action on that. You've got to decide that I'm going to hold most of those variables constant, and then I can view it as a single variable derivative, etc. The output variables, it's not really a problem, right? If you have multiple output variables, okay, take the derivatives one at a time. Having multiple output variables is really a simple matter. Okay, so with that as context, let's suppose now that again we have instead of multiple intermediate variables, what do we do if we have multiple input variables? Now keep in mind, my goal is to find the partial derivative of z with respect to xi. So how am I going to deal with the possibility that maybe there's other variables over here? And the answer is, good news, the exact same way we did with all other partial derivatives. Notice if I'm taking a partial derivative of z with respect to xi, that means we're doing a partial with respect to xi. That means that all of the other variables here are constant, right? I'm viewing, color choices. I'm viewing that variable as a function of these variables. Whichever variable is the one you want to take the partial with respect to, fine. Just hold all the others constant and go about your business. So hopefully, no surprise, you get the exact same formula as you do for the one on the previous page. The only difference is that these derivatives are now single variable derivatives. These previously single variable derivatives, because there was only one input variable x there, those previously single variable derivatives are now partial derivatives. Right? So these are now partials. Other than that, it's the same story, right? It's the same story with, we've got so many paths. This path gives you that term, et cetera, et cetera. And finally, that path gives you that term. Okay. All right. Okay, so here's a problem. What's different about this question is that here I'm giving you just an algebraic presentation of the question. And so what I want to strongly urge y'all to do, I think this is a big deal. Certainly it is for me. Everybody's mind works differently, so whatever. But for me, it's a huge deal to recognize that based on what's written here, I don't have a clear indication of, wait a minute, what's a function of what? There's so many variables running around. What if these equations were written in a different order? You know, you write a bunch of equations in a different order. It's still the same set of equations, right? So where's my diagram? So draw your diagram is the first step. So now you got to kind of go through the equations to see what they tell you. This says W is a function of P, Q, and C. Okay, that tells me this part of the diagram. This says P is a function of X and Y, but likewise all of these equations really tell me that P, Q, and C are functions of X and Y. So you make those observations, and then you realize I actually have a simple diagram of what's a function of what, and here it is. Okay. And with that being established, then the question becomes clear. Well, I want to take the partial of W with respect to Y. There's my input, there's my output. I can clearly see what my intermediate variables are right there in the diagram. That's my intermediate variables. Likewise, those tell you the paths through which changes are going to propagate, and likewise, those tell you the terms that you're going to have in your chain rule. Is everybody on board? Okay. All right, and then of course you got to actually crunch it out, right? I mean, so what are these partials, and put it all together. Okay. All right, y'all can do partial derivatives. Okay. Okay. Here's the completely general case. We've already considered multiple variables at that level, multiple variables at that level. Now, new question, what if there are multiple variables at that level? What do you do? We've already made the observation, output variables. If there's a bunch of output variables, okay, whatever. You just one at a time. The other output variables don't affect other output variables, right? So it doesn't really change things at all. But here, nevertheless, here's a sort of a generalized case that we might consider where we have several z variables that are functions of, let's say, several y variables, which are themselves functions of, let's say, several x variables. And again, we can talk about composing the functions like that. Quick observation while we're here. This is just a little heads up. Easy little landmine to accidentally step on. So be careful with this. It sort of looks backwards the way I write this. I wrote F compose G. It feels like G comes first because look, there it is. G acts first, doesn't it? So shouldn't G be first? Why did I write G second? Right? And the answer is, ultimately it's a sort of a weakness of the notation of math that I'm sorry we can't change. It's here to stay, right? But when you write a function and you apply it to something, the thing that you apply it to appears on the right. And so actually it makes total sense that, G does act first, and that's why I have it next to the input variable x. So you really have to do it this way, right? It wouldn't make any sense otherwise. In other words, let me write this a different way. It's f of g of x. So, my gosh, right? How weird would it be to write this as g compose f? That would just be horrifyingly weird. Okay. All right, so just keep heads up. It's just a little quick aside. Okay, so same formula. Now, I want to show you a different way to write it. I think this is very valuable as well. I'm going to show you some of those values. There's some nice interpretational advantages that come out of what's going to appear to be notation here at a glance. Right? I'm going to skip down here to the bottom of the page and ask, I hope y'all remember how to multiply matrices. If you have never seen matrices before, no problem. A matrix is just an array of numbers or expressions or what have you. And if you want to multiply two matrices to get another matrix, and if you want to compute, for example, a certain element in the ith row and in the jth column of the product matrix, then the rule is whatever row the desired element is, look at the corresponding row of the left matrix. And then whatever column the desired element is in, you look at the corresponding column of the right matrix. It's a weird rule. There are fantastic reasons for why we would want to make such a seemingly weird rule. And that's a subject of Math 216 or Math 221 or Math 218, if you're so inclined. Engineers will see this in 216. Anyway, so for the purposes of this course, I'm going to take this as this is just a given. This is the rule. That's how it is. And this tells you how to compute a given element of the product matrix. Okay, so with that context, come back over here for a second and recall that for this function, viewing the z variables as functions of the y variables, I can write down, recall was the wrong word. I'm going to choose to take this function and write down all of the partial derivatives in this form as a matrix. So this is a choice. We're going to call this the Jacobian matrix for that function f. The z variables as functions of the y variables. Now, why am I writing them down in that order? From a Math 212 point of view, because it's about to be super awesome in a minute. As of the moment, it's not at all clear. This is an arbitrary choice. Notice the pattern, though, that the output variables, so for example, z1, right? The entire first row is made up of the partials of z1, right? With respect to, notice, all of the y variables, right? So y1, y2, etc. through yn. Right? So there's a pattern there. And then likewise, as you go down, the second row is all the z2 partials, etc. And then finally the last row is all the zp partials. So notice that pattern. Be very careful not to accidentally transpose it. Not okay. It's got to be like this. If you accidentally transpose it, things go dramatically, wildly off the rails. Okay. So this is going to be a choice. We call this the Jacobian matrix. Now, then notice as well, I can write down for this function that gives the y variables as functions of the x variables, I can write down it's just by the same pattern, it's Jacobian matrix. Again, all the partial derivatives just written down in this arbitrary, but you got to give me highly methodical little manner, fixed manner. Okay, so here's the amazing thing. If you take those two matrices, those two Jacobian matrices that I pulled out of thin air as far as you're concerned, right? If you multiply them in this sense, if you matrix multiply, just like we do there, right? That product gives you a matrix that will, in fact, be per the same pattern, the Jacobian matrix of the composition. It's jaw-dropping that this weirdo little formula here actually computes all of your composition partial derivatives with one matrix multiplication. And let me just show you. You can see this in action. So let's compute this partial derivative, the partial of z1 with respect to xm, right? Let's suppose I want to compute that. Well, look, I've got a bunch of paths. That was a bad, let me draw better. There's a bunch of different paths through a bunch of different y variables. that gives me a bunch of different terms, right? And what do those terms look like? Okay, well, we remember the formula from the previous page. On the other hand, what happens when I do this matrix multiplication? Well, I will get this, I will get this row, that's the row that this is in, right? Dot, this column, that's the column that this is in. Row dot column, and then notice, check it out, as you do that dot product, this first path is the first term of that dot product. Right? Wacky. And then, you can kind of see it coming. The next, somewhere along the way, it's going to be that term of the dot product. Oh, come on. And then finally, this path corresponds to a term that gives you that term of the dot product. The dot product inside of the matrix multiplication reproduces the chain rule for each one of those product partials, or composition partials. So it's pretty darn cool. So let's consider our options. If you wanted to write down, okay, we've got all these different functions, and someone said, okay, here, write down a single formula that represents all of the p times m different partial derivatives of that composition function. A single formula. Well, you would think you'd have to write down p times m different formulas, but no, you don't. All you have to write down is that. That's pretty awesome. Okay. All right, so I like to point that out. I'm a big fan. Cool things we can do with that. While we're here, let me make a couple of neato observations. This is just for your consideration. I think it's a nice pattern to notice. But let's look at one of the row vectors here. Let's look at, for example, this row vector of that Jacobian matrix. That row vector, it's the vector of all of the partials of y1. Wait a minute, we've heard that before. All of the partials of a function with respect to all of the input variables, that's the gradient vector. So, neat fact, valuable fact, Jacobian matrices have rows that are always gradient vectors. And we've already seen that gradient vectors are super important. Okay. On the other hand, likewise, columns are pretty natural as well. They're what I'm going to call partial derivatives. So this one here, for example, this column here, that's all the partials with respect to x1. All the partials of all the y variables that are functions of the x variable. Of all the partials of y1 with respect to. Sorry, I'm getting my wires crossed here. I have a cold, so I'm a little hazy. All of the partials of all the y variables with respect to x1. So you might even say it's the partial of this g function with respect to x1. So that's a pretty natural thing as well. Okay. All right. Okay. What can we do with this? I mean, aside from being a super handy bookkeeping tool, formula organization trick, what else is this good for? I have several feelings on that. Here's my first one. Let's consider this composition. Now here we have a multivariable function. Several inputs, several outputs. I'm going to refer to the several input variables as an x vector. That's a vector in Rn. And the outputs I'm going to call the y vector in Rm. And now let's imagine precomposing, as we've done before, by viewing the x variables as all being functions of t. Now, I would like to take this specific context. Notice the peculiarity here is that there is exactly one input variable. That's the peculiarity here. And this gives rise to a very nice geometric picture, as it turns out. So here it is. A super cool geometric picture. By the way, here's the chain rule. This is the same old matrix chain rule that we wrote down on the previous page. Just writing down all the partials in that specifically organized fashion, and matrix times matrix equals matrix. There it is. Okay. First thing to notice, this matrix, as previously observed, it's all the derivatives of all the x variables with respect to t, otherwise known as the velocity vector. Right? So we didn't really think of this in those terms initially. We thought of this as we're just sort of composing two functions. But what I have there is literally a parametric curve in Rn. That's a parametric curve. That's a point moving around as a function of time in space. And the Jacobian matrix in this case is its velocity vector. How about that? So the Jacobian matrix is not just an algebraic thing, through matrix multiplication. It's not just a bookkeeping convenience, right? It is geometrically natural in this application. So that's pretty neato. Here's the other observation to make. The composition here, that composition, I've got y as a function of t. A bunch of y variables as a function of t. That's another parametric curve. And this Jacobian matrix, again, is the velocity vector there. So what we've got, let's see, zoom out a notch. We've got two parametric curves. Do it like this. We've got two parametric curves. We've got, by the way, this function that I haven't talked about yet, this function here, g, right? Notice that's a function from the space where the input parametric curve lives to the space where the output parametric curve lives. So that g function here, I'll do it like this. That g function is this right there, right? The green vector, this is the velocity vector for my input parametric curve that's floating around in R3 over there, Rn, the input space. And then this purple vector is the velocity of that output parametric curve floating around in Rm, the output space. Right? So this is I'm just drawing a picture now of what is the scene that we have, and what you can see. The point to this, the reason I show you this example is because of what this allows me to determine about the Jacobian matrix in general, and that is color. This Jacobian matrix. That Jacobian matrix is telling you how to relate input velocities in green to output velocities in purple. Right, so if we temporarily now sort of ignore the precomposed, function of t business, what this is saying is, look, if for whatever reason, if you're in the domain and moving with a certain input velocity, and you would like to know correspondingly what is the output velocity, I mean, surely if you're moving in the input with some velocity, this point gives rise to that point. As that point is moving in the input space, that point in the output space is going to also be moving. If the input has a velocity, then the output's going to have some sort of velocity, right? And the Jacobian matrix here is the thing that allows you to connect them. The Jacobian matrix turns input velocities into output velocities. And again, let me call way back, right? Some time ago when we first started doing derivatives, I made the observation we're going to talk about a bunch of different kinds of derivatives in this class. And they all have their moments and their uses and their, points of view, etc. And that I had a favorite. This is it. The Jacobian matrix, right? In full generality, no matter how many input variables you have, no matter how many output variables you have, the Jacobian matrix thing that I have in blue is the relationship between input velocities and output velocities. Or likewise, input changes and output changes. Velocity is just a form of change. Right? So that's our cornerstone point of view on derivatives. Right? It's a relationship between input changes and output changes. Well, I mean, this is going to be hard to beat for fully addressing that sort of relationship between input changes and output changes. Yeah.
So what could you
almost like put in that black box? Like, let's say, could it be something like, I don't know, the formula for air resistance as a way of relating like an input velocity?
Listen, all you need is a function here. Right? You just need to be able to view some variables as functions of other variables. And, you know, when will you need to view input variables giving you output variables? Well, and we talked about weather, you know, early on, and we talked about, you know, economics, you know, risk and profit, and maybe several other things, the functions of interest rates and capital and labor and whatever, right? So, I mean, the applications are limited only by your imagination. Yeah, it's extremely general, extremely applicable. Yeah, totally. Right. Anybody else? Okay. All right. So, another quick reminder, you may recall when we first started writing down partial derivatives, and I made the observation that a lot of students like to hang their hat on partial derivatives as fundamentally that's what the derivative is, and that everything else is just tools that we build up for, you know, specific applications. And I think that's a mistake. I think this is where you should hang your hat. In terms of, like, not in terms of computation, perhaps, of pros and cons, different situations, but in terms of intuition about what fundamentally is a derivative of a multivariable function. Well, I mean, this wins, right? Multivariable function, if you've got possibly multiple input variables, possibly multiple output variables, how do I relate input velocities to output velocities? Well, here's the answer. It's Jacobian matrix. So I like to think of the Jacobian matrix as fundamentally default, you know, cornerstone idea on derivatives is the Jacobian matrix. And then, okay, there are special cases that are nice. Velocity vectors are nice. They're a special case of a Jacobian matrix. Gradients are kind of nice in some situations. Those also are a special case of a Jacobian matrix. Partial derivatives are the little atomic little bitty items that make up the Jacobian matrix. But the Jacobian matrix is the derivative. Okay. All right. Right. Okay. Now, with that point of view in mind, now this is just a point of view. I like this a lot. And if you're looking for satisfaction, you might say in terms of, wait a minute, how did this work out that the partial derivatives over here ended up being products of Jacobian matrix? Was this just lucky, or, that seems arbitrary, perhaps. Okay. So this is what gives me some satisfaction on that, and that is to imagine now a scenario where I have two fully multivariable functions. So I'm going to think of a bunch of y variables as functions of a bunch of x variables. And then after having done that, I'm going to plug the outputs into here. I have a bunch of z variables as functions of a bunch of y variables. We'll call that function f. And I can talk about this composition, right, that turns the x's into the z's directly. Okay. Well, all of that observed. This is just this can be a real hand wavy sort of an argument. But look, if I take off in the domain space here and start moving with some velocity, and if I then say, okay, well, as I move in the x world, then of course that g function is going to make y move also. The thing that relates those two velocities, the thing that relates the x prime vector to the y prime vector is this Jacobian of g. Excuse me. Oh my gosh, the Jacobian of that g function. Okay. Well, likewise, now, given that we now see y is moving with a certain velocity, well, wait a minute, the y is the input to this f function. If y is, in fact, moving with that certain velocity that we just computed, that's the input to f. If the input of f is moving with some velocity, then, well, the output's going to be moving correspondingly with a velocity. And the relationship between those velocities is that Jacobian matrix. Okay, so what? Who cares? Well, we have a scenario where x, y, and z are all moving with certain velocities. And I can talk about how to compute blue from green, and I can talk about how to compute yellow from blue. But I can also ask, look, I don't really care about blue. I just want to go straight from green to yellow. How would I do that? Right? What allows me to compute, in some sense, both steps at the same time? Well, look, the first thing you're going to do is you're going to multiply by the Jacobian of G, and then immediately after multiplying by the Jacobian of G, you're going to then multiply by the Jacobian of F. Right? That's what you're going to do. Right? You're going to first multiply by the Jacobian of G, and then, secondly, multiply by the Jacobian of F. Which means you're going to be multiplying by the product. So the composition here, that Jacobian of the composition, well, it's what you get by successfully multiplying by those two matrices. So you might say that the entire matrix chain rule comes out immediately from just an observation about how the Jacobian treats input velocities and output velocities. So I think this is a super point of view to take. I really like this, so I hope you'll kind of digest. It's good for geometric intuition and satisfaction, and for these purposes. Oh, while I'm here, let me go back to another point. Remember how I said that we're going to be drawing a lot of pictures that are not graphs, right? That's not a graph. This is not the graph of G. It's also not level sets of G. It's also not, G isn't parameterizing a picture or anything like that. This is that weird little point of view on functions that we talked about and kind of looked, sort of side glancingly at of, let's draw the domain over here and the target over here and then just look at one point at a time. Well, that allows us to make this very natural observation about how stuff moves in just in different worlds. Okay. So, off of Jacobians now, and back to just individual partials. Let's talk about second derivatives. First, here's a first derivative. Now, everything that's on the screen right here is something we've seen before. We've got z as a function of x and y. And here's our specific formulas. Here, z is a function of x and y. And now let's consider what would happen if x and y were themselves functions of r and theta. And we could ask, how do I view z as a function of r? And, well, we've got two different paths along which changes can propagate. That gives us two different terms, right? And this is all just straight up exactly what we've done previously. Nothing new. I'll point out that in this case, where not only do we know that z is a function of x and y, but not only do we know that x and y are functions of r and theta, but I know exactly how x and y are functions of r and theta. And that allows me to actually compute these partials here. So let's go ahead and take that additional step. Okay. Is everybody on board so far? Let me call your attention to the notation that I'm using. I kind of switched from Leibniz notation over here to this Newton-like notation that I promised would be handy at some point. This is, I think, a nice, starting to look like a nice example anyway. Okay. So let's talk about a second derivative then. Right? I've got a formula for the partial of z with respect to r. What if I wanted to know the r partial of that? How do I take the r partial of this existing r partial? Now let me show you what a lot of students like to figure, and that is, as a first step, to say, well, looks like we're going to be using the product rule. I see here I've got this thing called zx, and I guess I'll take the partial of zx with respect to r, and I guess I'll write that as zxr. A lot of students will write zxr. And let me just point out that makes no sense at all. It really doesn't. ZXR is not a thing. I'm going to emphasize this I'm going to write down Z, X, R, and then cross that out with a frowny face. That's not a thing. Let's think about what that would have to mean if that were a thing. That would suggest, okay, partial derivatives. Okay, so we're going to hold all the other variables constant. But wait a minute. What are the variables? If I have to hold all of the other variables constant, then I've got to see, well, what's a function of, what are the actual input variables, and then from that decide which of them I can therefore hold constant. Well, if Z is a function of X and Y, then I can't talk about the R partial of that Z, thought of literally as a function of X and Y. On the other hand, if I think of Z as a function of R and theta, then I can't talk about its partial with respect to X. It just doesn't make any sense. Right? So when you're taking a partial derivative, you've got to keep in mind you're taking a derivative of a function. Like when I'm talking about these partials here, for example, I am actually taking a derivative of this guy. Right? It's that function right there. That's the thing I'm actually taking derivatives of. That function has clearly indicated input variables, X and Y. R is not one of them. You see what I'm saying? So don't write down something like ZXR. It doesn't make any sense. It's meaningless garbage nonsense. And graders tend to have a negative view of meaningless garbage nonsense. Right? So keep that in mind. Okay, so how do we deal with this? Here's the big idea. Now, of course, I am going to, we've already agreed, I'm going to take this ZR. There it is. That's ZR. And I want to take an R partial of it. And there remains this awkwardness of, okay, but there's still a ZX there, and I've still got to have to deal with finding an R partial of it. If I can't just write it as ZXR, then what do I do? And the answer is to realize that ZX is actually a new, I'm going to treat it as a new variable. It's like a new function. Quick appeal, if Z is a function of X and Y, I mean, what happens when you take a partial derivative of a function of X and Y? Well, you get a function of X and Y, different function of X and Y. So this thing ZX is a function of X and Y, and let's just be honest about that and just write it down. And there it is. ZX is a function of X and Y. I'm appending, supplementing my diagram. Right? And having recognized that ZX is a function of X and Y, it now kind of leaps off the page how I take the partial of that ZX with respect to R. I've got a chain rule problem. I've got various paths of propagation, right? I've got X as an intermediate variable and Y as an intermediate variable. And I'm just going to write down the chain rule as it applies to that composition. There's no mystery, really. You just have to be careful about how you interpret what's a function of what fits in where on the diagram. And by the way, let me take another, I'm going to pitch. Again, aren't diagrams nice, right? The diagram, I feel, is the thing that allowed us to straighten that out, right? Okay. All right, so you'll notice first a little quickie simplification. That's a constant as far as an R partial is concerned, right? If you're taking a partial with respect to R, theta is constant. That means cosine theta is constant. So you factor that right on out. Likewise over here, sine theta, constant. And here we go then. This partial derivative of ZX with respect to R it's going to be this thing. There's the propagation path through X. And there's the propagation path through Y. Straight up chain rule. That's pretty much the story on second derivatives. Just heads up for situations like this. Always have your diagram written there to keep track excuse me, of where you are and what you're doing. And make sure to, that when you find yourself, again, it won't necessarily leap off the algebra for you, right? But always think about what you're doing and taking derivatives at various points. And if, in fact, you are taking a derivative that is a chain rule problem, if there are intermediate variables, then okay, well, just make sure your diagram is supplemented and just write down the chain rule. That's all there is to it. And everything else in the rest of this solution, is just details. The partial of zx with respect to r is there. The partial of zx with respect... sorry, I gotta have myself. Partial of zx with respect to r is there. The partial of zy with respect to r, that shows up over there, is then likewise just this. Right? Again, two paths, two terms, and then off you go. And then, look, there's a couple little details here. Notice partial of x with respect to r shows up again. Don't forget, that's x is r cosine theta, so we can crank that out immediately. Do notice that here's another little second derivative partial. Now, we're hopefully a little hesitant to just zxx, but notice there's no chain rule there. Z is right there. It is a function of x and y. So taking a partial with respect to x, okay. Subsequently taking a partial with respect to x, fine. That's the second derivative. That is the xx. There's nothing to simplify. It's not a chain rule problem. Okay. And then, keeping track of notation. So there's a certain amount of details here. But other than that, it's pretty... it's just a matter of being organized and careful. And I will... one last thing, and then we'll call it a day. Don't try to go too fast on these questions. It's very common to, try to take maybe 3 steps all at once or something, go straight to there. You're going to get confused. You're going to lose a factor of cosine theta or something, right? So nice and slow. Space out your algebra comfortably. Right, so that you can see. I like to be able to, this is just, strategy at this point, but I like to be able to comfortably see what turned into what in the algebra, just because otherwise I fear that I'll drop terms or drop factors or, make up new terms because I got confused because I was doing too much in my head all at once, right? So lay things out, take pity on yourself, lay things out generously on the page. Right? It takes a little bit more space, but space is cheap. And don't go too fast. And there you go. Okay, all right. See y'all later. Have a nice day. Okay, have a good weekend.